Hey guys, welcome to my series of lecture. So today we are going to discuss mainly on the uniform and non-uniform doping. So as we progressed through all the things like charge neutrality across all the intrinsics and eccentric and also compensated semiconductors. So today in this class we are majorly going to focus on the uniform and non-uniform doping. So first part, let's focus on n-type uniformly doped. So let's take a profile where this is the distance and this is the profile of the charge carrier. The charge carrier profile across the semiconductor device. This box is a semiconductor device. So here we are taking uniformly doped thing. So for n-type, we know that this is how we will representing the charge carriers. So here if you see, so across the semiconductor, the charge carrier is constant. So there is no difference or there is no concentration gradient is happening. So it resembles what? So there is no concentration gradient. So dn by dx which is equal to 0. So we have already gone through this concept. This concept is indirectly contributing to what? Diffusion current. So diffusion is majorly depend on this parameter. So if this is not happening, then the diffusion current I diffusion will be equal to 0. So I diffusion will be equal to 0. So then this is what, there is no external because we haven't supplied any external battery sources. So E vector which is also equal to 0. So if this is equal to 0, then drift contribution will also be affected. So here what will happen? I drift will also be equal to 0. Okay, so comparing all, the I net will also be equal to 0. So this is the final observation that we are behaving. So what is the observation is that for uniformly doped n-type material with no external battery supply applied, the net current flow will be 0. So this is just in equilibrium state. So nothing, no external disturbance or internal disturbance is happening. So this is what one observation that we are getting over it. So let's discuss further, like what we can discuss is we can discuss this with the other external things like the similar thing for the p-type and n-type also. So let's take the second parameter which is nothing but the non-uniform doping for the n-type. So here the second one is the non-uniform doping. So last we discussed about uniformly doped, right? So here non-uniformly doped n-type. So non-uniformly doped n-type. So here take an example. So here the same thing, like we are considering a semiconductor device across the charge potential. So this is the distance and this is the gradient of a concentration axis. So this is x and this is n of x. So here we can also consider those to be nd of x. Depending upon the parameter given, we can take it. So here if we consider there is some kind of charge gradient is there. So if we travel across here, there will be some difference in potential. Here that is highly doped, here is lessly doped. So here we can see that dn by dx which is not equal to 0, means that is non-zero parameter. So this will, what will happen? This will contribute to some diffusion of electron. So electron diffusion will take place because this is the majority charge carrier is n-type. So based on this, what will happen? Some internal electric field will be built. So internal electric field will be built. So that is also not equal to 0. So it will be in the direction which is opposite to that of electron movement. So there is some kind of electron diffusion happening. Because of that, some internal electric field will also be produced. So based on that, some kind of charge carrier will be available for the electron to jump into the higher state in the EC level. So comparing to the last day, here we can see some kind of diffusion effect is there. So based on this diffusion, so IN diffusion will not be equal to 0 here. So IN diffusion will not be equal to 0 here. So then one more time, because of the movement of charge, the internal electric field is built. So based on this internal electric field, there will be IN drift will also be there. IN drift, which is also not equal to 0. So there is two kind of current is acting. So one will act in this direction, that this will act in this direction because of electron movements in this direction. So because of this electron movement, an electric field will be developed in this direction, not to the opposite, because we need to know why this potential is created. Because this potential is created, because this here is the positive charges will be accumulated, here negative charges will be accumulated. So because of that, from positive to negative, some internal inbuilt electric field will be generated. So because of this electron will move, some electron will move in this direction. So that is the current produced by this one. So this will be in this direction. So the equilibrium which need to be attained, right? So if we compare both things, so both is in opposite direction, so we will get the I net here also 0. So this is also equilibrium. So why this is equilibrium is that here you see this is then charged material. So nothing, no electrical supply, no temperature increase, nothing is happening. So no effect, no cause, no effect. So that is it's following the thermodynamic principle, or it's following the natural principle, that no cause because there is no effect. So no cause, no effect. So that is what the principle it is following. So when we can get some internal electric field developed is that only when there is an external electric field that is applying. Then only there will be some chance for the electricity to build. So let's take an example that I net which is equal to 0. So this is the equilibrium condition. So let's take this in J net also, like current density, which is also equal to 0. So there is two things, right? So Jn drift plus Jn diffusion. So Jn drift and Jn diffusion. So if we apply the formula, then Nq mu n E plus J d of n dn by dx. So these formulas you guys are already gone through detailedly. So if you guys haven't watched, please go and watch it. So here we need to find the electrical internal electric field that is developed. So if we keep here and we are moving this to that side. So then electric field which will be coming is minus dn divided by, let's divide these two terms, that is n and mu n. Q will be getting cancelled. So dn by dx. So this is the final formula that we are keeping. So the internal electric field that is built because of the electric electrons which are moved by diffusion, which will be equal to minus 1 by n dn by mu n. Why I am making there is this is Einstein's relationship. So we can even cut short and write it. So dn by dx. So the internal electric field which can be written as minus Vt 1 by n dn by dx. So we can use some differentiation formula and we can also remodify it to some other term. So it will be equal to minus Vt. So 1 by n can be defined as a ln. So d of x of ln n of x. We are making this n and x into n of x. So this is one term. So if we differentiate it, what will happen? So ln anything, if we differentiate by ln, then it can be written as 1 by this term. So that is 1 by n. Then this term is a function of x, so we can written as a dn by dx. So that is what we have written here. These three formulas, the three like two we can say, these two are very important. So you have to remember this. Even you can derive this by using this. If you guys even can remember this, we can directly substitute in the formulas. So this is the one kind of important formula that we can go through. So this is E of x. So if we need to find V of x from this, then we can simply integrate it. So integration of E of x over the distance will be equal to potential. So this formula also we know that electric field is the negative gradient of V. So this thing we know, right? So from this only we are attaining this one. So if we need to find out the V in that the threshold voltage that is developed because of the electron diffusion, then we need to integrate this one over the dx. So then we will get the voltage potential. So that thing also we will cover in the upcoming lecture. So from this lecture what we have seen is the uniform and non-uniform doping. So if uniformly doped, then there will be no current movement. Even if it is non-uniformly doped, then also no current movement will be happening because the semiconductor is in equilibrium state. So let's take a condition to find out the internal electric field that will be developed in the non-uniformly doped n type. So that is the case that we are came up with the final conclusion formula of internal electric field developed. So if we need to find out the voltage, then we can integrate it with a negative to find the voltage that is developed. So while going through the PN junction diode, we will be completing going through this one. So for now, let's remember this, how these coming, how the derivation and how the calculations is going. From next class, let's get into other topics interesting. Let's continue the uniform doping profile over other P type and other things also. Thanks. Stay tuned for next lecture. Like, share and subscribe the channel.